Hi everyone. Today we are hosting Guy Evan for the talk. Guy.
Thank you very much. It's a pleasure. I'll be talking about some data structures. This is joint work with Ioana. Please stop at any time for questions if something is not clear, so that this talk is a bit less boring. Okay. Um, Let me just overview what a dictionary is, what a filter is. You have a universe, we denote it by capital U. Its cardinality is given by lowercase u. And our goal is to maintain a representation of a data set D, which is a subset of U. And we want to support operations such as insert, delete, query. In a dictionary, the issue is that we want to maintain the set in a precise fashion, namely whenever we're giving a membership query, we're supposed to answer correctly. And in a filter, we are just representing membership in an approximate manner. Namely, if X is a member of the data set, you are always supposed to say yes. But if X is not a member of the data set, then you're allowed to say yes with probability, which is bounded by epsilon. Okay? And the whole point in using filters rather than using dictionaries is that you can save space by using a filter. I'll get to that in a second. I want to talk about three models or three settings. One is called the static one, the incremental one, and the dynamic one. In the static case, you have a fixed data set, and basically all you want to do is you want to support queries. In the incremental setting, you want to support queries and insertions. And in the dynamic setting, you want to support both queries, insertions, and deletions. Now, we will use this parameter n to denote an upper bound on the cardinality of our data set. Okay? Now, the reason that people are interested in filters is because you can reduce the space. Okay? So, there's a typo here. Let me fix it. If you look at a static dictionary, then it has to somehow represent n elements out of a universe of u elements. So if you want to represent such a set, you would need log base 2 of u choose n bits. And that translates to n times log of u over n plus a linear number of bits. Okay, so this is a lower bound on the number of bits you need in order to represent a subset from a universe U with cardinality n. And if you want to use fewer bits, then the filter helps you, because the lower bound for a static filter, you plug in, instead of U, you plug in n over epsilon, and then the lower bound becomes n plus log of 1 over epsilon plus big theta of n. And this is true. What I wrote here is true if epsilon tends to 0 as n tends to infinity. If epsilon is constant, then there is a lower bound by Lovett and Porat that states that in a dynamic filter, you cannot, with a constant epsilon, you cannot do better than C epsilon times n times log of 1 over epsilon, where C is some constant that depends on epsilon that is greater than 1. So the point that I want to make in this slide is that the number of bits per element basically in a dictionary is log of u over n, and in a filter it is log of 1 over epsilon. So you can reduce the number of bits per element if you use a filter rather than a dictionary, and then you pay by having this probability of a false positive event. And another thing I want to emphasize is the probability of a false positive does not depend on the data set. It depends only on the random choices that the filter makes.
Okay. Can I ask you a question?
Sure.
What's the intuition behind dynamicity costing us some extra constant?
You mean in this lower bound?
Yeah, the last one, yes.
I don't remember. They do some kind of reduction to a dynamic graph problem, and they show some property there, but I do not remember the details of why making it dynamic increases, in some sense, the lower bound.
But this is something, I mean, to get the thing, this is something like 1 plus epsilon or something of this flavor, right?
This
Or
this fellow, of course, tends to 1 as epsilon decreases. Yeah.
okay, okay.
Yeah. Good. So now you may ask, what would be our design goals when we are talking about small space? So suppose I have a data structure problem, let it be dictionary or filter, whatnot, and let's denote by B a lower bound on the space. We say that the data structure is succinct if the space that it requires is 1 plus little o of 1 times B, where the little o of 1 tends to 0 when n tends to infinity, the size of the data set. And we say that the data structure is space efficient if it is succinct plus an extra linear term, namely we allow an extra constant number of bits per element. And the difference between a succinct and a space efficient data structure is very subtle. It appears only when when the lower bound is superlinear. Okay, so for example, in the dictionary, it occurs when u over n tends to infinity. In the filter, it happens when the 1 over epsilon tends to infinity. Okay, so we will have this extra linear term in the space, which means an extra constant number of bits per element. And that in the what I consider to be the interesting cases of the dictionary where the universe grows faster than n, or where the epsilon tends to 0, is the same as being succinct. Good. The model of computation that we're talking about is called the word RAM model. Every memory access, either a read or a write, transfers a word, a block of bits of length log u. Okay, so you can read an element in by one memory access, and all basic computations over words require constant time. Namely, you can do addition, subtraction, multiplication, division, shifting, selecting, and stuff like that in constant time. Okay. I will be talking a little bit about multisets. So let me just define what I mean by a multiset. I mean, you all know what it is, but let's just define it for a second. A multiset is a set with repetitions. It can be represented by a function defined over the universe, and this function assigns a natural number to every element, where m of x is simply the multiplicity of x in the data in the multiset. The cardinality of the multiset is the sum of the multiplicities. The support of the multiset is the set of elements whose multiplicity is positive. Okay, and of course we can and we will talk about dictionaries over multisets. If you have a dictionary over of a multiset and you insert an element 3 times and you delete it once, then its multiplicity is 2, and you want to remember that that's its multiplicity. But what happens in filters? What does it mean to have a filter that maintains a multiset? Well, that in fact is called in the literature a counting filter. There's some delay here. That is called a counting filter. A counting filter approximately maintains a multiset in the following sense: that when you do a query, it returns an answer which is not smaller than the actual multiplicity, and it will not be equal to the actual multiplicity, what is called overcounting, with a probability which is bounded by epsilon. And this is exactly, a generalization of filters that approximately maintain a set. Okay? Any questions about what a counting filter is? Okay, so if an element has multiplicity 5, a counting filter is allowed to answer 6, but that would be considered like a false positive. Okay, good. Now, if you want to design a filter, the simplest way to do it is to use a dictionary. And this is a reduction that was presented back in 78 by Carter et al. Um, and what they suggested was to use a random hash function that maps the universe to a set of cardinality n over epsilon. We refer to h of x as the fingerprint of x. And because this function is random for every x, which is not indeed, the probability that it collides with one of the elements in the data set is bounded by epsilon. Okay, so then you get that if you have a filter, if you want to build a filter for the data set D, then it suffices that you build a dictionary over the set H of D, the image of D under the function H. Now, this reduction applies also not only in the static case, but also in the incremental case. Okay? And if your dictionary is space efficient, your filter will also be space efficient because the dictionary space will be n times log of u over n. U over n is just 1 over epsilon. So it will be n times log of 1 over epsilon plus a linear overhead. Okay, so you get a space efficiency. Okay, so we have this simple reduction, and we're going to play a lot with this reduction, but let's see what its pitfall is in the dynamic setting. Okay, so can we support deletions? Suppose I have two elements, x and y, that collide under H. So H of x and H of y both equal z, and the filter is asked to insert x, insert y, delete y, and then we have a query over x. What does the dictionary do? Well, the dictionary inserts the image of x. The image of x is z, so it inserts z. Then it inserts the image of y. The image of y is also z. Then it deletes z because it wants to delete y, and the image of y is z. So you inserted two copies of z, deleted one copy of z, you query z, and the question is, will the dictionary answer yes or no? Right? Will it say that z is in the set or not in the set? Well, if you want the dictionary to respond correctly, then the dictionary must support multisets. It must know that z had a multiplicity of 2, and this deletion only decreased the multiplicity by 1, and therefore this query should answer yes. Okay? And in fact, Pepe Rao back in 05 used a design for a dictionary for multisets in order to obtain a dynamic filter. And it remained an open problem that was, again, phrased by Arbitman, Naor, and Segev back in 2010, of how to design a dictionary for multisets that is dynamic, space efficient, and performs operations in constant time in the worst case. Okay, so we're talking about worst case constant time. Yes, please.
How would multisets help here? I mean, still be unable to distinguish between having. I mean, imagine you have a sequence of operations: insert x, insert y, delete x. And then, depending on whether the query is over x or over y, you
saying suppose the last query would have been query of y rather than query of x, right?
Yes.
Then that would be a false positive. That's okay.
Okay.
That's fine. Yeah. Mm-hmm. Some probability that such an event occurs that's due to collisions is fine.
Okay.
This, right? You would have this phenomena even if you didn't insert x and you queried about y, right? Which is fine. Yeah.
Okay. Good. Now I understand.
Yeah. Thanks for the question. Okay. So our first contribution was that we noticed that this reduction of how to use a dynamic filter using a dynamic dictionary does not actually require the dynamic dictionary to support arbitrary multisets. It suffices if the dynamic dictionary supports random multisets. And the reason is that the image of a data set is a random multiset, where a random multiset is simply, you insert an element X uniformly at random, and you delete an arbitrary element X in your data set. So let me elaborate on what it means to design a dynamic dictionary for random multisets. But before that, I want to make sure that once we have this creature, we get for free a dynamic filter. Okay? So this is, there are two parts here. One is, it's not clear what this means as a dynamic dictionary. And the second question is, why does this help us design a dynamic filter? Okay, so I think the second question is easy. Let me talk about the first question. Okay.
So can I have a question?
Yes, please.
Guy, can I have a question? Okay, so yes. Do you assume something about your hash function? Do you assume that it has some kind of independence properties?
I assume that the hash function is perfectly random. This assumption needs to be relieved in practice, and you need to use hash functions that have a sublinear representation and can be computed in constant time. This is a very important question, and it has been solved, for example, by Albit Mano and Segev, and we outline in our in one of our archive papers, we outline how that can be done in this specific setting. But the answer is yes. Yeah.
Okay.
It's very important. But for simplicity, let's assume that the hash functions are perfectly random and ignore how they are stored and how they are evaluated. But indeed, this is a major question. Okay. Good. So what does it mean when I talk about a dictionary over random multisets? Okay, so I'm thinking of the input as if it's driven by an adversary. So what can the adversary do? It can ask for an insert, but it doesn't insert a specific element. It has no control over which element is going to be inserted. So in fact, it asks a black box to insert an element, and the black box picks an element uniformly at random, independently of the previous insertions. Okay, so you have a sequence of elements xi which are uniformly at random, chosen uniformly at random, and are independent. Now the adversary can query on any x it wants. It doesn't matter. The adversary actually does not know which x's are in the set or not. And then when it wants to perform a delete, the adversary cannot actually ask to delete a specific element because it doesn't have a clue which elements were inserted into the dictionary. What it can ask is to delete an element that was inserted at time I, and that element is of course denoted by x of I, but it doesn't know, the adversary doesn't know what x of I is. Now this whole description is incredibly synthetic and contrived, but what it models is what we need in order to get a dynamic filter using the reduction of Carter et al., which uses a hash function from the universe to n over epsilon. Okay, so this is a kind of a strange thing, but it means that if we want to design a dynamic filter, then the only thing that we need to do is to design a dynamic dictionary for random multisets.
So does the adversary know what element was inserted, or is it not known?
No, H is hidden from the adversary. Yeah. Okay, so the first result is a dynamic filter for sets that this event of overflow means that when you begin, you design this filter for a specific epsilon and for a specific n. And overflow means that if you allocate some memory, and during the course of the execution of the algorithm over a polynomial sequence of operations, the space is not enough. So for some reason, at some parts, you don't have enough space. That's called an overflow. And the probability of overflow is small. So with high probability, you don't have any overflow. High probability meaning here 1 over polynomial in n. Okay? For every operation, I can complete the operation in constant time in the worst case. And I'm space efficient. Space efficient meaning this is the number of bits I need per element, 1 plus little o of 1 times log of 1 over epsilon plus a constant. And this solves the open problem of ANS, Abitmanov and Segev, regarding the design of a dynamic filter. Okay? Now, the way, of course, we obtain this result is by designing a dynamic dictionary for random multisets with the same type of properties, right? No overflow with high probability, constant time worst case per operation, and space efficient. Okay, so I'm left with describing how to support random multisets, how to design a dictionary that supports random multisets. Okay. A second issue is the design of counting filters. Recall, a counting filter is a filter that approximately maintains a multiset. And here, if we use the same type of reduction, we get that the dynamic counter filter for M can be obtained by a dynamic multiset dictionary for H of M. And here, M is arbitrary, and therefore H of M is no longer a random multiset. For example, think of M as being a set in which the element 1 appears n times. Then clearly H of M is not a random multiset. And now a dynamic dictionary for multisets that works in constant time in the worst case for all operations and is space efficient is an open problem posed by Abitmanov and Segev. And in fact, Pepeval back in 05 designed a dictionary for arbitrary multisets, but insertions and deletions there are not worst case constant time, but expected amortized constant time. Okay, so you want to design a counting filter, and for that you need your dictionary that supports arbitrary multisets. And our second result is a counting filter for multisets, where you have a bound on the cardinality of the multiset, and again, overflow with you have no overflow with high probability. Every operation is constant time in the worst case, and you're space efficient. Okay, same type of flavor, but the difference is that it's a counting filter, and the method is now, instead of designing a dictionary for random multisets, the method is to design a dictionary for arbitrary multisets with the same type of characteristics. Okay, that would be the second result. Any questions about the first two results? Okay, so just to give you a flavor of what was done previously for sets in the area of dynamic dictionaries, there are dictionaries that are fast but not space efficient. These are important. I'm going to use them, by the way, in my construction. I'll specifically use the last one here, which is a paper by Abitmanov and Segev from 09. Okay, this is a paper one before their paper in the year 2010. And there was a whole...
Can I interrupt you?
Sure.
So why? So it's like your second result doesn't imply the first one.
It does.
It does.
Yes.
Okay, so it's a generalization of the first one.
You're asking, why am I wasting your time, right? Why am I stating it as two results if the second result is superseded by the first result? So first of all, I wanted to check whether you were listening. That's the first reason. The second reason is, and this is something, a little bit practical, the constant here. The constant number of bits per element is bigger in the arbitrary multiset construction than it is in the random multiset construction. Okay, so there's a difference in the constant. But yeah, thanks for the question. You're absolutely correct. Okay, so there are dictionaries that are fast but not space efficient. You can see some interesting papers here. There are dictionaries that are space efficient but not fast. Namely, in the worst case, they require super constant time. And these are not going to help me, but the first type I need. You'll see the second why. And again, for sets, there are dictionaries that are both fast and space efficient. There's one here by Haman Rao, which is constant time in an amortized sense. But the Albert Manal Segev paper from 2010 does resolve this question. Okay, so it gave a dynamic dictionary with constant time per operation, worst case, and that is space efficient. Okay, in fact, succinct. What about filters? What can I tell you about filters? What works in the world of filters? So Pepe Rao in 005 designed a filter which is space efficient, but insertions and deletions are not constant time in the worst case. They are expected amortized constant. And Abit Manor and Segev in 2010 do not support deletions. So they're only in the incremental setting, not in the dynamic setting. So the gap was achieving all these things together. Space efficiency, worst case constant time, and supporting deletions. Now, the literature has literally hundreds of filter designs that come without a proof. Okay? Literally hundreds of designs. Okay. What about counting filters? What do we know what did we find in the literature about counting filters? So there are two papers that come without any worst case guarantees. One is called the summary cache by Fancao, Almeida, and Broder. The other one is called the counting Bloom filter by Bonomi, Mitzelmacher, Panigrahi, Singh, and Varghese. There is a paper that comes with worst case guarantees, but it's very similar to a Bloom filter, and therefore the number of memory accesses is log of 1 over epsilon, so it's not constant if epsilon tends to 0, and it's not space efficient. And this is called a spectral filter by Cohen and Matias, and it has nearly 500 citations. Okay, so these things attract attention somehow. So before I go into details, I want to show you two very easy cases, okay? The first case is that I want to design a dynamic filter for the special case in which epsilon is very small, okay? Epsilon is so small that log of 1 over epsilon grows faster than log n, okay? Now, why is this an easy case? So what I want to do is I want to employ a retrieval technique of Ditzfeld-Binger and Pei from 08 that works as follows. I attach what is called a value or a satellite data to every element, which is given by my fingerprint function. And this satellite data is log of 1 over epsilon bits long. Okay, and it's of course a random function. Now I can do insertions, deletions, and queries because it's a filter, and I use a dynamic perfect hashing as a black box. And this dynamic perfect hashing gives me, if X is in the subset, it gives me a hash code for X. If X is not in the subset, it either gives me a fail or it gives me, a hash code of another element. I don't care which. But of course, the perfect hashing has no idea of what this FP function is. Okay? It's a black box that doesn't know what the FP is. Now, I use the hash code as an index to an array that stores fingerprints, and I store their FP of X. So now when I want to query X, I compute the hash code. If it's fail, I say X is not in the data set. If it's in the hash code, I read whatever is here, and I will give you the fingerprint of X. I will compare it, by the way, with what it should be. It might be fingerprint of Y. I compare it with what it should be. If it's the same, I give it as the answer. If it's different, I say X is not in the set. Okay? Now, this construction, the dynamic perfect hashing, has space which is n times log u over n plus log n. And then you have this extra array which has n plus little o of 1 times n entries, and each entry is log of 1 over epsilon bits long. So this is your total space. And your u over epsilon is, your log of u over epsilon is, what am I trying to say? Yeah, this log of 1 over epsilon behaves bigger than log n, and this u over n is polynomial in n, so this whole thing becomes immaterial, becomes negligible, and this is the major part, and you become space efficient. Okay? Any questions about this? So this is like a easy case. For some reason, people in the literature did not point out that it was already solved in some sense. Okay. There's another solution, but let's okay. Another easy case is if you want to manage multisets using a dictionary, and again, you're looking at the case that u over n, log of u over n it grows faster than log n. So this corresponds to the case where you want to design a counting filter with log of 1 over epsilon being omega of log n. And the solution here employs two dictionaries that store keys and values. You could use, for example, ANS09. Recall that ANS09 is a dictionary that is fast but not space efficient. It is what is called, I think, compact. It's 2 times the lower bound, and something like that. Yeah, it's a constant times the lower bound rather than 1 plus little o of 1 times the lower bound. You use two such dictionaries. So here's D1 and here's D2. The first dictionary stores at most n elements, and it stores the elements whose multiplicity is bounded by log cube n. So it will use the value, this is satellite data, it will use this value to store a counter. And the counter will require log of log cube n, because log cube n is the maximum multiplicity of an element in this dictionary. So the first dictionary is what we call for light elements. Okay, so these are, let me write, light elements. Light elements. The second dictionary is for the heavy elements. These are elements whose multiplicity is at least log cube n. Therefore, you do not have too many such elements. And here you need log n bits in the counters. So the value that you attach to every element is log n bits long. And now you use these two dictionaries, and together you coordinate them, you insert an element, you see what its multiplicity is, you decide whether it goes here and here, and you do the space calculations for these dictionaries. And why did I write here? Yeah. You do the space calculations for the dictionaries, and this is the space that you will get. And because log of 1 over epsilon, log of u over n is so big, this is the largest part, and this thing is negligible, and this thing is negligible, and you get space efficiency. Okay? Any questions? Good. I think that I confused myself. This is ANS10.
So I'm just confused a little bit. So why log cube? Why not log?
You could have done it with log squared, right?
Okay. Yes.
Yeah.
Good.
Again, I wanted to check that you're all alert. No, I'll use log cube again later. It's just a number. It doesn't matter. Anything which is bigger than log n. Yeah, you're absolutely correct. True. Okay, good. So now we're left with the main part. We call this the dense case. The dense case is when u is, log of u over n is big O of log n. Okay? The first case was when it was little omega of log n. Now it is big O of log n. That's the complementary case. And we want to design dictionaries for multisets, which are either randomized or arbitrary. And this would be the dense case. So we're left with the main part. Okay? Good. Running out of time. Good. The dictionary overview, how does this thing work? It has 2 levels, the first level, the second level. The first level consists of many, many bins. Each bin is a dictionary for a small set. And whatever doesn't have room in the first level goes to the second level, which is called the spare. We refer to this as an overflow of the bin. This is not an error that you have an overflow of the bin. The error happens when you have an overflow of the spare. Okay? Now, the spare is a tricky dictionary because the spare is a dictionary for arbitrary multisets. Because the fellows that overflow have some dependencies between them, and you cannot make any assumptions on the multiset, even if originally the x's came from a randomized multiset. Okay, so you use a random hash function to map the elements. These are the elements. To map the elements to one of the bins. And once a bin is full, you send x to the spare and you store it in the spare. Okay, let's look at this general architecture for designing a dictionary. Okay. Now, a first technique which appears back in Knut's old technique called quotienting is when you take your element or your fingerprint. Here it's described in the language of filters. You take your fingerprint and you partition the binary string into a quotient and a remainder. The quotient is log n bits long. The remainder is log of 1 over epsilon bits long because your whole universe is n over epsilon. And now what you do is you store this element in an array. In the entry q, you store the remainder r, where this is the quotient q and this is the remainder r. Now, an issue that arises immediately is that you may have many r's that you need to store in the same queue, and then techniques such as linear probing, decoding chains, bound and run lengths, all that stuff comes into play. Okay? We will not use any of this stuff. Okay. A second issue is you want to manage these bin dictionaries, which are small set dictionaries. For this, we propose a dictionary which is called a pocket dictionary. So basically, you want to store these pairs qi, ri. Every qi is from a certain range. Every ri is from a certain range. And you want to do it, as we said before, you have an array. And these are R1 and R2 have the same Q. R3 has this Q, and so on and so forth. And maybe some of the Qs do not have any Rs that belong to them. And we want to store this small set. And the solution is to use a variation of an encoding called the Elias-Fano encoding. This is back from the 70s. And the same type of encoding also appears in the Carter et al. Paper. It is called the Exact Membership Tester 2. So let me tell you what that fellow is. Of course, we discovered it independently, but I would say some 40 years later. This is the solution. We call it a pocket dictionary. The reason we call it a pocket dictionary is that the whole dictionary is supposed to fit in a word, so that every operation over the pocket dictionary can be done in constant time. And how does this dictionary look like? Well, you have a header and a body. The header stores the occupancies of the queues of the entries in the array in unary. So A1 has 2 elements, you write 1, 1, and then you write a 0. A2 has 1 element, you write a 1, then you write a 0. A3 has 0 elements, you write just a 0, and so on and so forth. And your body is just a concatenation of the remainders, where you take the remainders in lexicographic order of the elements, of the Q and the R. And the space that you need, well, you need one bit per element. You have 1 0 bit per quotient. So this is B plus n prime. And then for every remainder, you need log k bits, and the number of remainders is n prime. And if you think of B and n prime as roughly the same thing, then you have 2 bits plus log of 1 over epsilon bits per element. This is part of the lower bound, the log of 1 over epsilon, and this is the extra 2 bits that you pay. Now, you have to pay something above the log of 1 over epsilon. The distance between the entropy and 2 is less than half a bit. Okay, so you're not wasting too much here. Okay, good. A second technique is to look at the load balancing, right? So let me go back to the architecture. We want to analyze how many elements which are assigned to bins cannot fit in the bin and have to go to the spare, because we want to bound the size of the spare. So if we want to bound the size of the spare, we look at throwing n balls into m bins, and this is the x-axis tells us the bins, the y-axis tells us how many balls fell into each bin. We put a threshold, which is slightly above the average occupancy, and we hope that the number of balls that fall above the threshold is small. Indeed, if you set the parameters correctly, if the average occupancy is logarithmic, and you have some over-provisioning, which is given by this parameter, which is little o of 1, and you set the threshold to be 1 plus delta times b, then the number of balls that are here, in this shaded area, the number of balls that are delegated to the spare will be bounded by n over log cube n with high probability. And this means that your spare is storing little o of n many elements, and therefore you could implement the spare using a dictionary which is not necessarily space efficient, because you have a lot of slack here with the log cube. Okay?
Okay, can I have a question?
Yes, please.
So I am a little bit lost in these calculations. So are we talking about classical balls into bins, or are you doing some powers of 2 choices, or?
No, this is classical one choice.
Okay.
Classical one choice. I can reduce the size of the spare by using power of 2 choices. Since you raised the question, I'm answering. I could reduce the number of bin balls that are assigned to the spare using power of 2 choices, and this would be nice because the little o of 1 would become smaller. The problem is that the analysis of balls into bins in the dynamic setting, where you delete balls and not only insert balls, is not so good. And then we do not get favorable results. So that is an open question. Okay, Václav, this is for you. Open question. Analyze the occupancy, even the maximum occupancy of bins in the dynamic setting, in the power of 2 setting, in the power of 2 choices paradigm. This is an open question. The analysis is pretty weak.
So if I understand correctly, you are relying on the fact that with a single choice, the process is basically memoryless. Basically, if you remove the element, if you remove the ball, it's like you have never inserted it.
Yes, this is a major point. I will go into it in a second because it becomes tricky when you talk about dynamic versus incremental setting. But definitely what you're asking is incredibly important, because there's a difference between the incremental and the dynamic setting. And definitely in the power of 2 choices paradigm, the system, the configuration has memory. And when you do deletion, you are snapshotting a configuration which is not one to be achieved in the incremental setting. Yeah, this is the obstacle in the analysis of the power of 2 choices, which doesn't occur in the single choice. Absolutely. Okay, so let me elaborate on this issue. So what does it mean? We analyze the number of balls that fall above the threshold, and in the incremental setting, it just tells us that the spare does not overflow. But in the dynamic setting, a ball may stay in the spare even if its bin is no longer full. Right? So now you do a snapshot of your configuration and you see that the bin is not full, yet the ball resides in the spare. Okay? So does our analysis crash or does it stay valid? Okay? So this is an interesting question. And in fact, in Abid Manao and Segev, what they do in order to reduce the dynamic setting to the incremental setting is that they pop balls back from the spare into their bins once the bin become non-full. If you have a vacancy in a bin, then a ball that resides in the spare goes back to that bin. They do it, by the way, in a lazy fashion, but that's a cute trick. But from the point of view of analyzing the size of the spare, this is what they do. And that's the way they reduce the dynamic setting to the incremental one. Now, in our analysis of the random multi-set dictionary, our analysis is strong enough so that there's no need to pop. Okay, so we show that over a polynomial sequence of insertions, deletions, spare will never overflow. It will always stay below n over log cube n, and you don't need to do any pops. And in our arbitrary multi-set dictionary, our analysis is not as strong, and therefore we need to perform pops in order to get the reduction from the dynamic case to the incremental case. So I do not know, I cannot tell you for sure that this had to be the case also in the multi-set dictionary, that you need to do these pops, but this is what we were able to get. Good. So now let me summarize, how does the dictionary for the randomized multisets look like? Okay, so we have the bins, we have spare. Inside the bins, we store duplicates. We store mx copies of x in the bins if there's no overflow in the bin. Okay, so if you have like 3 or 4, say, copies of an element, you store these 4 copies in the bin as if they are different elements. Okay, a pocket dictionary has no problem to store copies of the same element. And in the spare, well, the spare is going to be a key value dictionary in which the value is going to be the counter, the multiplicity, and that requires log n bits. But we have no problem with these log n bits because very few elements are stored in the spare. Okay, so we get a nice, fast spare, which is sublinear in space, and our bins can accommodate these duplicates, no problem. And we implement the bin dictionaries using the pocket dictionaries. And that more or less summarizes the construction for multisets and implies our dynamic filter. Okay? Now, what do you do when you have arbitrary multisets? Now, if you have arbitrary multisets, this is not quite the same case as you have in the randomized case, because in the randomized case, you don't have the full spectrum of multisets with high probability, right? Here you could have a situation where there are no duplicates. The support is the same as the cardinality, namely M is a set. And you could have the other extreme where the support consists of a single element, namely there's one X which has n copies in your data set. Now, if you have to accommodate this case where multiplicities might be very high, then you say, okay, let's use counters, and counters will have log n bits. But if they have log n bits, then you have n times log n space, which means you're not space efficient. So you have to do something in the middle. Okay, so let me explain what we do. Again, we distinguish between light and heavy elements. Light elements are elements whose multiplicity is bounded by log cube. Heavy elements are the elements whose multiplicity is at least log cube. We store the light elements in bins with variable length counters, and we store the heavy elements in the spare with log n bit counters. So we have to use variable length. We have to adjust, we have to adjust to the multiplicity of an element. Well, it's not so easy. Let me elaborate a little bit more on how we do this. So we have our bins in our multi-set dictionary. We store the elements in a pocket dictionary, and we store their multiplicities using variable length counters. Now, we have to make sure, as before, that the pocket dictionary fits in a constant number of words. And we have to make sure that the counters also fit in a constant number of words. In fact, for the purpose of the analysis, we give a somewhat tighter bound on the sum of the lengths of the counters. And of course, we're only talking about the light elements, so their multiplicity cannot be bigger than log q. Okay, so this is what we try to do in our bins. And we have an invariant. And the invariant says we will store x in the spare at time t only if one of the following holds. Its multiplicity is high, it's heavy, or the bin is full upon the insertion of x and remained full since then. And there are two sources of fullness of a bin. A bin can be full either because its pocket dictionary is full, or because the sum of the length of the counters becomes too long. Yeah? Whenever one of these conditions holds, you put it in the spare. Whenever all of these conditions do not hold, you have to pop x back to its bin. Okay? And this invariant, because of the popping, reduces the dynamic setting to the incremental one. Okay? Good. So now we have our analysis of the spare. We want to show that the spare does not overflow. We want to claim that the spare will have big O of n over log cube n elements. Well, you have three types of cases. The heavy fellows, or not too many heavy fellows. You have the fellows that overflow because the pocket dictionary is full. This is the same analysis as we had before. And you have an analysis for the variable counters becoming too long. How do you analyze that? Well, this is analyzed using a balls into bins paradigm with a logarithmic weights. Instead of counting the number of balls in each bin, each ball comes with a weight, and its weight is logarithmic in its multiplicity. Okay, so this is a new variant of an old question of balls into bins. It's also analyzed using Chernoff bounds and these type of.
So the weight is the logarithm of the total number of balls in a bin, or
the weight of an element is the log of of 1 plus its multiplicity rounded up. Okay.
Mm-hmm.
Good. Sorry. Button. How much time do I have left?
I mean, we can take a few more minutes.
Okay.
So actually, can I have a question?
Sure.
Can we go back to this balls into bins? Because I'm a little bit lost. So could you maybe repeat like one more time? So what is the variant of balls into bins that you need to solve? So I understand that you have these weights, right? But like what is the precise statement?
The precise statement is that I'm asking, when does it happen when these xi's, I want to see that you can see it. Yeah. When I look at these xi's that are thrown into bins, and I sum their weights, and I look at the event that the sum of the lengths of the counters is, say, bigger than 12 times b. And I want to ask, how many balls are sent to the spare when this condition, due to this condition? I want to show that the number of balls that due to this condition are sent to the spare, or the number of elements, is bounded by n over log cube n.
Okay. And one more time, what is b?
B is, you could think of B as log n. It's actually log n over log n. B is the number of elements that are stored in a pocket dictionary.
Mm-hmm.
Yeah? So I would say this is more than B element, distinct elements. This is the capacity of the pocket dictionary, and here we have some constant, say 12 times b for the sum of the lengths of the counters.
I see.
Okay.
So intuitively, the worst case should be where all the weights are 1, right?
Yes. Yeah, that is because of the concavity of logarithm.
Yes.
Definitely.
Okay. Thanks.
So let me, switch gears. If you lost me, this is a good time to recap. There's a whole issue which is called extendable data structures. And this issue relates to the situation in which n, the number of elements that you are, maintaining in a dictionary or whatnot, you don't know it in advance. And what you want is you want to have, again, fast operations, and you want your space to be small as a function of n of t. So the point is, this is the time axis, this is the number of elements, and the number of elements varies over time. It's a very dynamic setting, and you want your space to adjust to the cardinality of the set that you are now maintaining. Okay, and the first example of such a data structure is called extendable arrays. It appeared in a paper by this is Brodnik, and I don't remember most of the other names. I'm sorry. Carlson, Demain, Monroe. I don't remember the other names. And by Rao and Raman. And the point is that you want to maintain an array with n of t entries and the type of operations that you want to support. As usual, you have a read and a write. You want to find out what is the contents of the ith entry, and you want to write into the ith entry some element t. But here, up front, you don't know what the size of the array is, so you want to grow it. So grow says n of t equals n of t minus 1 plus 1, and shrink means that you decrease the size of the array by 1. And these data structures support operations in constant time, and the space they require is almost optimal because it is nt times r. R is the number of bits in each entry of the elements. And then you have this overhead, which you can see is sublinear. Okay? Kind of amazing result. Okay?
So can you say, like, in one sentence, what is the idea, how you get this thing?
The point is that as you are growing in time, you can allocate or deallocate memory in larger and larger chunks and charge for it. Think of a...
So this is amortized complexity.
Yeah, but then the trick is how to de-amortize it, of
Okay,
course.
I see.
Yeah. Definitely. Yes. Thanks for attending my talk, Václav. Really, I appreciate it. So
at the end of the day, it is worst case, right?
Yes.
Okay.
Yes. Now you want to design dynamic dictionaries that are extendable. And here there are some papers. You see here that the space is not optimal in this paper. Who's the D? I don't remember. The T is Tarjan. One of the M's is Melhon. I don't remember the other names. I'm so sorry. The space is n log u, and the time is constant in expected amortized. Raman Rao present a succinct succinct space, a constant time per operation, except for updates, which take constant expected amortized time. And the last iCalc, there's a paper by Lu et al., but it's not dynamic, it's only incremental. Okay? So what I want to talk about is an extendable dynamic dictionary. It's our third result. It supports overflow. It overflows or fails with a small probability. Every operation is constant time in the worst case, and the space you see. This is the part which is succinct. The 1 plus little o of 1 times the lower bound. The lower bound varies over time. It adjusts to the size of the data set. But we have an overhead. We have a log n bits of overhead per element plus a constant. And you fight for this one. This one that you see over here is, you fight for it. This is why we separate between the log n and the linear term, because we're fighting for this one. Okay? Good. And another topic I want to talk about is perfect hashing. Okay, so you could presumably obtain perfect hashing by a dictionary. Perfect hashing means you want to assign a value, a hash code to the elements, so that these hash codes are an injective. They are one-to-one. So you could use the element location presumably to serve as the hash code of an element, but even if you have a dictionary that does all operations in constant time, it is not clear that these hash codes are good, because what happens in the dynamic setting or even in the extendable setting, right? So stability, something that people like in hash codes, they want them to not to change during the interval between the insertion and the deletion of an element. And let me show you that this is perhaps not so trivial. Think, for example, about the pocket dictionary, where I have these remainders appearing one after the other, and now I am deleting R1. I'm deleting X1, and R1 belongs to X1. So I need to delete R1, and that means I have to shift all the remaining remainders up by one position, and they all change their location simultaneously. Because a shift is a constant time operation, but I change all these locations simultaneously. There's a super constant number of hash codes which have changed in one operation. Something which we don't like. Yeah, it's not stable. So let me suggest a definition of stability of hash codes in the dynamic and in the extended setting. Okay, and I think this is an interesting contribution. The first definition I want to present is predictable hash codes. So what is a predictable hash code? Each element at every point of time has a hash code. The hash codes are, of course, one-to-one, but they may change over time. But they change in what we call a predictable fashion. What does that mean? It means that there exists a function f such that for every 2 points of time, t2 and t1, I can derive the hash code of x at time t2 from the hash code of x at time t1 and the cardinalities of the data set at time t1 and t2. Okay, and that will be predictable, because if you give me this hash code and I know what the cardinality was here, I know what the cardinality is now, I can figure out the current hash code. Okay. Second definition is almost predictable. Almost predictable means it's predictable, except that in every time unit, I may change the hash codes of a constant number of elements. So I have a subset S of t whose hash codes may change, but this subset S of t is constant. And it is reported by the data structure. So the data structure will tell you, oh, X3, X5, and X17 have just changed their hash code. This is their new hash code. Okay. With respect to this definition, we have the following result. We have a dynamic extendable dictionary with hash codes. The hash code range is linear. Overflow and fail occur with small probability. Every operation can be completed in constant time in the worst case. Notice that we have this hash code operation, which you give me X and I tell you what its hash code is. In the incremental setting, the hash codes are predictable, and the space is this 1 plus little o of 1 times the lower bound, plus 2 plus little o of 1 times nt times log nt, plus a linear term. So per element, I have the optimum plus 2 times log n plus a constant. And in the dynamic setting, I don't give you predictable hash codes, I give you almost predictable hash codes, and the space here increases from 2 to 3. Okay? So, let me summarize with open in further problems. Václav, this is for you. Analysis of the power of two choices for the heavy loaded case when you have deletions. Second question, reduce the overhead, this little o of 1 term. Add operations such as successor, predecessor, whatnot. And let me point out that we are working on improving our extendable dynamic perfect hashing so that it works with hash codes which are not in linear range, but in a 1 plus little o of 1 linear times n range. Okay? Thank you very much for your attention and persistence.
Okay. We might have time for one quick question.
I'm sure Ioana has a question.
No, I don't have a question.
Oh, yes, you do.
Shemek, my name is misspelled.
Her question is, why did you spell her name?
Does that mean that I can misspell yours now, Shemek?
I think you already do.
No, I just Google it every time. I actually put in the effort.
Okay, if there are no questions, I will just stop the recording now.
But I do have a dumb question.
Okay.
Thank you.
So I've been thinking, like, do people try to relax the notion of filters, let's say? Like, for example, in the definition of filter, you allow to have false positive with some small probability. So what happens if you also allow for false negatives, for example?
So that trivializes the question. That this question was addressed in the Carter et al. Paper. To feel silly about it trivializes the question. Yeah.
Okay.
Also, I must say that for the applications people have in mind for filters, false negatives are much more severe than false positives. Because
Okay.
false positive means you are going to look up into the database and eventually find nothing there. For false negatives, you're going not to look up and realize that there was something for you to be found.
Okay.
Yeah, and right, and the applications where filters make a lot of sense are usually where precisely you're trying to shorten the space of a dictionary. So it happens that you can tolerate these false positives, which means you get a much smaller data structure. Sometimes the filter is actually used to interact with the dictionary so that you don't imagine that the dictionary is stored on external memory. It's huge. You don't want to access it too often. And so you use a filter to make sure that you decrease the number of sort of useless queries, which would be the queries for which you would ask the dictionary for an element that is not in the set.
Yeah, now that makes perfect sense. Yeah.
Yeah. So then,
Okay. Thank you, guys.
Pleasure.